Okay. All right. Hi, everyone. Some quick announcements this morning, afternoon, I guess now. First of all, remember that the tutorial is due, not the tutorial itself, but the one sentence description is due today. So please fill it out today if you have not yet. If you don't really know what you want to do, that's okay. This is meant, you're meant to be unconstrained. We will provide some feedback at this point. So we will provide some feedback. But just go ahead and submit something. If you submit nothing, that's very hard to provide feedback. So submit something you're thinking about. Sky's the limit. You really can do whatever you want, and we'll try to recommend. Either say just okay, that sounds good, which I hopefully will do that to most people. For the most part, we don't want to be too restrictive here, but we might make some suggestions too. Secondly, homework 3 is going to be out this Wednesday as normal, despite the fact that the next homework is still ongoing. That was kind of the trade-off. There will still be a homework released on Wednesday. Whether or not we extend that one, depends on the material we cover, et cetera, and probably also how well the auto graders go in the first few days. But we'll try to make that. Fingers crossed. It'll be due 2 weeks from Wednesday. Any questions about logistics? Yeah.
Should the tutorial be something related to our background?
Right. So the question was, should the tutorial be about something related to your own background? It certainly can be, but it does not have to be. You are free to explore a new topic or talk about something that you know very well.
Okay.
As long as it's in the data science context and you can't give a tutorial on, I don't know, how to play tennis really well.
Or can it be something that we find very fascinating and just like rant on about it?
The question is, should it be instructional or can you just rant for 2,000 words? You should be instructional. It should be framed as trying to teach someone else this topic or a small slice of the topic. Yeah.
So does it need to have exercises as well for the
Right. So the question is, does it have to have exercises? No. It should have code and prose mixed together, but they can be code that a person would then transcribe rather than an explicit auto grade or test for any sort of mini assignment with the tutorial. Yes. Yeah. So the question was, can the tutorial be related to the project? And yes, that is fine. I saw the one there. Let's see. So the question was, does it have to be in Python, this library? We are requiring that you use the IPython notebook as your interface. Now, it actually is possible to use other backends that are not Python for that. I haven't actually thought about that one yet. My inclination would be to say that part of your grade from this will come from other students doing it, right, going through your tutorial and essentially grading you. If it's in a language they don't know, that could be very hard. So my inclination would be to say, let's do it in Python. And if there's no library, if there's no bindings for Python, maybe you could write some quick bindings or something like that for your topic. I'll think about that because you're right, that seems a little bit overly restrictive, but because they're being shared amongst the class, I might go ahead and enforce it to be in Python. Yeah.
Borrow like our own code that we've maybe written for like an interview or something like that is on the data public and like restructured to an instructional format.
I see. So the question is, can you borrow some of your own code you've written previously? I don't know. Let me think about that a little bit. I think, so a little bit is fine. Yes, if you've written little parts of it, that's fine. If you've written a major sort of blog post or something like this that essentially covers the exact same thing, and you kind of transcribe that, I prefer you did not do that. Now, I'm not going to necessarily go looking for all the blog posts you've made in the past to see if it overlaps, so I probably won't find out if you do that. But the goal will be to develop something new, some new content for this. If it's a small snippet of other code you've used before, that's fine. Don't worry about that. But if you're copying the entire code and text, then no, you want to create something new for this course. Yeah?
What about in the other direction? Like, make something really cool for our tutorial and wants to make that into a blog post?
Yeah.
Is that allowed?
So the question was, can you then blog about your tutorial? Yes, absolutely. The idea was actually that these would be made public for people that didn't object to that. So we would love it if you wanted to then go and advertise your particular tutorial more widely. We could even link to it from the class webpage, which hopefully as time goes, it will build more content and get more hits and such. So yes, absolutely. Maybe we'll codify those things also in the document and update the document a bit. It was a little bit sparse right now. Well, we can update it a little bit to hit all these points. Okay, so before I jump in, I wanted to mention one thing because there was a little bit of confusion last time. So I want to take 5 or 10 minutes or so and just, well, hopefully 5, and highlight one thing people found confusing last lecture was this compressed sparse column format for matrices. And I think I did a bad job because the sizes of a matrices were just happened to be almost the same, such that it was actually kind of unclear what was happening. And you thought there may have just been a typo in the slides, there wasn't, but it was a little bit unclear. So I want to go through a quick example of that right now. Eric actually also posted a note of this on Piazza. So hopefully between my explanation now and the note, you'll be able to figure it out. But I just want to highlight this because I think it actually ties together nicely the ideas behind sparse matrices and graphs. So say we have a matrix like this. Not very sparse, but let's just say we have it for the time being. The sparse matrix format, the compressed sparse column format, is arrived at in the following way. For the data array, we just pick all the data in order in column major order. So this would just be 1, 2, 1, 1, 2, 1, 3. Right? So pretty simple. For the row index, array, this is also very simple. You go through the same order and you write down the index of the row that element appears in. So this appears in the 0th row, 1, 2, 1, 2, 0, 1. Okay. Now, and this is the same as the tuple format, so just happened to be ordered in that way, so hopefully it was pretty intuitive to everyone. Now, the difference here is in the column index, because the column index here, unlike the row index, and unlike the column index matrix in the tuple format, is actually not indicating which column the different elements are in. It's not indexing into the columns of this matrix here. What it's instead doing is saying it is the size of the number of columns plus 1. So there's going to be 4 entries in this array. And each one is going to point to where in these arrays that column starts. So the 0th column starts at the 0th entry. In fact, the 0th column is always 0 typically, but we have it there for sort of convenience of access here. So the column 0 starts at index 0 in these 2 matrices. The next one, the next column, so column index 1, starts at the 3rd element in these matrices here. So this would be a 3. The next column, column index 2, starts at the 5th element here. And then the last entry in this is just the end of that column, so it would be 7. It would be 1 more plus the last index in the other one. And by the way, this is always the last number here is also always the number of non-zero entries that we have in that matrix. So that's the format. And the interesting point I want to draw, the interesting sort of analogy I want to draw here is, suppose you were asked to build a adjacency list format for a graph, for a static graph, we'll say. We'll say we're not going to be adding or removing elements. And remember, let me go actually to my slides here, which I'll flip back to in a second. I was going to this. But you remember our adjacency list had this kind of format where we had a bunch of, we had a list of all the nodes and then a pointer to a list of the nodes that one was connected to. Okay. It turns out that this format is essentially exactly what you would do if you tried to implement that in an efficient way. So here's what I mean by that. So this column index is kind of like the first column here. It just effectively indexes over all the nodes. I mean, I'm not listing them here because it's implied that this is, node 0, this is node 1, this is node 2, and this is node 3, right? So I'm not, those are not, that's just the index in that array. And then for each one, what this points to is this points to a location that lists all the outgoing edges. So this is 0, right? And that would say, that would be pointing into this array. At location 0, there is a list of the outgoing edges for that node. The data would be, say, if there's like a weight to these edges too, that could be that. But just worry about these two entries first. Okay? The next entry, and by the way, how do you know how many entries there are? Because you know that this next element here points to the next column, so there have to be 3 minus 0 entries, 3 entries in that array for column 0. Similarly, the next one, this is a pointer into this array that says where are the outgoing edges in that array to nodes 1 and node 2. Okay? So there's a very strong connection here between sort of how you would build a data structure for a graph and how you would build a data structure for a sparse matrix. In fact, they're actually the same thing, right? I mean, in a lot of ways, actually, a lot of the algorithms people use for sparse matrices are based upon graphs. And this really is a matter of just setting up a data structure in the right way. So in the homework for the 688 problem, you have to build a graph representation that uses an adjacency dictionary. And I'm asking that you use this, I think, well, I guess that isn't actually required, but I would think most people are probably using that for their implementation of Dijkstra's algorithm. But you don't have to, actually. You could also use a compressed sparse column format to implement Dijkstra's algorithm, and it would actually be a little bit more efficient if you wanted to do it that way, because it's kind of a very quick and fast format for these graphs that says exactly for every node what are the outgoing edges there. So that's kind of what's nice about these formats is they translate very, very easily into graph algorithms. Now you don't have to do that. I would actually recommend using the sparse dictionary, using the adjacency dictionary, just because it is a little simpler, and looping over the keys and those things are a little simpler than trying to query into a SciPy sparse matrix format. But fundamentally, if you wanted the most efficient algorithm possible, you would actually use something like this. Probably once your graph was finalized and constructed, you would translate it to a format like this, and then kind of go from there. Yeah. Yeah.
And this is essentially a parallel to the adjacency list.
Yep.
Their performance be
Yeah, so the question was, shouldn't their performance be the same? You're absolutely right. They're both the big O notation is the same for them. They're both constant time lookups to get the number of outgoing edges. The difference here is whenever you look up into a dictionary, you have to hash something. You perform a hash query, which just takes some time. Actually, for sort of weird reasons in Python, if you're hashing on keys, it actually doesn't take any time. But it still adds more work, especially if you're hashing on non-integer indices. So this is just sort of like the raw operation, most efficient way to do it. If you want to implement it in C, you should do it this way, not with a dictionary. All right, so let's move on back to graph algorithms. So I covered these very briefly last time, but I want to just sort of go over again what these things were, and then also highlight an example for Dijkstra's algorithm and for PageRank, but then also go on to the next one, which is the Girvan-Newman community detection algorithm. And now, as I said, these are 3 kind of not randomly picked. They're very important algorithms, but they're by no means the current state of the art, nor are they, well, Dijkstra's algorithm kind of might be in some cases, but they aren't oftentimes the current state of the art when people actually do. I mean, Google is not anymore based just upon PageRank, and there are much more efficient community detection methods than Girvan-Newman. But it is the case that these things kind of historically played a very important role in bringing out graphs and graph networks as kind of a data science fundamental tool. And so I do want to highlight these because I think they bring up three very important and separate topics in graphs. Okay, so we went over last time the shortest path algorithms and Dijkstra's algorithm. For those who don't remember, Dijkstra's algorithm essentially worked by the following. We're given a graph. We have some set for each node. We have this array D that says how far is every node from the source node. And initially, this is always, actually not initially, but this is always going to be an upper bound on the true distance. Initially, for the source, it's set to 0. For all the others, it's set to infinity. And we proceed, and we also build this, this set Q of all the vertices in the graph. Then we do the following. We pop off, we extract the vertex from Q that has lowest score, lowest distance under D. Now that operation takes one line to write in pseudocode there. It's actually not that simple, right? Because how do I store a set here of where I can always find the smallest distance element in another set, and I can then update that distance in the other sets too. It's not at all actually easy. The way it's done internally is usually with a heap to be most efficient. For theory, actually, you should use something called a Fibonacci heap with Dijkstra's algorithm, but we're not ever going to actually do that in practice. A simple binary heap works pretty well. For the assignment in 688, there's actually a structure called heapdict that I would recommend everyone use for that. I guess you don't really have to use it, but it makes your life a whole lot easier if you do use it. So I would highly recommend that. But anyway, assuming we can do this in our one line of code here, that we can just, assume we pop these things off. We pop off the element with the smallest, remove the element from Q with the smallest distance. And then for all its outgoing edges, we set, or all the nodes that are linked to it by outgoing edges, we set that distance to be whatever the minimum is between its current distance. So if it's already shorter than this, going around the path, we don't update it. But the minimum of that, or our distance to node I plus 1, because we're assuming the graph's unweighted, so that every step takes one step to get there. And that's the algorithm. If you also want to not just compute the shortest distance, but also the actual path itself, you have to be do a little bit more bookkeeping. But actually, all you have to do is just store which of these two options was taken. And if you do, in fact, the shortest path was, in fact, through node I, you have a pointer from this node J to node I, sort of a back pointer to say the shortest path to this node went through this other node. And you can trace then shortest paths in reverse to find the shortest path from the target or from the source to the target. I'm omitting that because it's actually very similar to this, and you'll have to do it anyway if you're in 688, or doing those problems at least. Okay, so let's just keep a simple example now of all this. I imagine it's pretty straightforward to everyone. You've probably seen, or not probably, a lot of you have probably seen something similar to this, Dijkstra's algorithm or something similar before, so I think it hopefully is not too complex here. But on this simple graph here, I thought I used a directed one. I guess I'm using an undirected one here. No, I'm using the directed one for PageRank, that's right. So to start off with, we're going to have our source A. We want to find the distance between A and all the other nodes there. To start off with, our distance array is 0 for A because we're already there, and then infinity for everything else. I don't know why I switched the order of Q and D in subsequent lines, but sorry about that. We pop off node A. And then what's left in our queue, I'm using the word queue here sort of unintentionally, in our set queue is just the nodes B, C, and D. And now when I update the distances from that, I can get to nodes B and C from nodes A. And they are currently infinity. So I'm going to set their distance to be 1 now, because the distance is 0. It's the distance between node A and that plus 1. That's the minimum between that and infinity. So they get the value 0 for their distance there. Next, I pop off B. I B actually does not update anything because B doesn't, the min of my current distance at C and B would be the current distance at C, so I would not update the distance for C, and A also I would not update the distance for, and everything remains the same. Then I pop node C. My queue now just contains element D. These become the distances, and finally I pop node D. Distances stay the way they are, and the queue is empty, so we're done. It's important that we have to pop each element off always. You don't get to stop early before you're done popping them all. So you will have to go through every single node and then do additional work because for every single node you have to also look at its neighbors potentially. So it does take some work, but it's not too bad. The official complexity depends on what data structure you use for this queue here. So I won't go into that, but it's at least on the order of the number of nodes plus some other work like maybe log v or log e and things like that. I don't think log e actually ever figures in, but it's you have to go through all the edges at least once, you have to go through all the nodes at least once, and then you have to do some extra work to pop that off, which we're not going to worry about here. Any questions with this? Okay. Yeah.
What are the best structures in Python to use for this? I mean, like this set is C++ or something like that, where you can add and remove vertices just using data.
Yeah. So the question was, what's the best data structure for that queue? It's not just a set. Even in C++, it would not be a set because it has to be a sorted set, or not even a sorted set, but it has to be a set where you can always pop off the minimum element in that set, and where you can actually update scores because I'm changing the scores, the priorities of these things as I'm going through it. So the algorithm, the data structure that you use is called a priority queue, but it's a priority queue. It's called a find decrease priority queue because you have to be able to find elements in the queue and decrease their priority. Actually, you don't have to increase them, but it's called, I think. And there are various implementations of this. Heapdict is actually doing exactly that in Python, so it's a reasonable way of doing it. Yeah?
For weighted, it would be exactly the same except you had the weight, right?
Yes, the question was for weighted, it would be exactly the same, and yes, exactly, it would be the same, except you add the weight here instead of 1. Now, the caveat to that is if there are negative weights, then this thing gets nasty. It will not give you a solution anymore because there could be infinite cycles where you would have infinite negative costs, and this will not do that because once you pop something off, it never goes back on the queue. So it does not work for negative weights, but it will work for arbitrary positive weights. Okay, let's talk about PageRank next. So you remember that I talked about this notion of important nodes in a graph, and there's some sense in which the central nodes here seem to be more important than the edge nodes, right? Because they seem like they're more central to the graph, or I don't know why they're more important. Are they more important? I guess. And unlike shortest path, the thing I mentioned was that there's no real answer for importance, right? We just assume that whenever we define an algorithm, it is telling us what the importance is. And the PageRank algorithm is one method for determining what the importance or the relevance of different nodes in the network are, famously used by Google to rank their search results. So I'll go over it just briefly because I already described it once, but the idea is started a random node in the graph, randomly jumped any of its neighbors. If the node has no outgoing edges, you actually just jump to a random node again. Otherwise, you'd always end up, right? Otherwise, if you follow this process, you would always end up in one of these nodes that has no outgoing links, and you would just stay there forever. And when you're browsing the web, if you find a web page that has no outgoing links, you probably don't just stay there reading it forever. You probably jump to another random page, or maybe you go back. But that's not what it models. It models just staying there forever. No, it models jumping to a random node in the network instead of staying there forever. And then you optionally also jump just any time, even if you have outgoing links in that node, you jump to a random node with probability D. And by the way, the reason for this is this avoids a problem when you have things like long chains. So there's a very long chain in a graph, something like this. So imagine some rabbit hole of web links here. leading you down, where each one only has one node. PageRank, if you do this, it would assign them all and say, the first node has a lot of important links going to it, right? So what it would do if you do this is it would assign all of these the same weight as this one, right? Because if I go here, I always have to go here, and then here, and then here, and follow it until the very, very end. So they would all actually have the same rank, even though this one seems more important than the rest, right? And so to avoid that, they have this random D factor where with probability D, and that's usually I think it was originally 0.15. I think I'm using 0.9. I'm going to use 0.9 just because the numbers come out a little bit easier. Sorry, 0.9 for 1 minus D. So D is 0.1. D originally, I believe, in Google was 0.15. And so this avoids this problem, right, of sort of getting stuck in an infinite path and having these all be important nodes, even though they seem less important as you go along. And this D factor makes them less important. So the algorithm is really quite simple. We start with the adjacency matrix. We replace the 0 columns of A with 1. That would basically involve us taking anything that has no outgoing links and saying it has an outgoing link to everything. And that simulates this fact that when we hit a dead end, we jump randomly to any other node. And then we normalize the columns of A. Now, importantly, if you actually implement this, and you are going to implement it, the people doing the 688 problems at least, you do not need, you can in our example, but you do not need to actually fill in the 0 entries with 1s. You can actually do that kind of more efficiently directly with sparse matrix operations, but conceptually what you're doing is you're filling it in with 1. You actually definitely cannot create a matrix where with that D term it's blended into the matrix, because that's the matrix of all 1s, right? It's saying that at any node we have some probability of jumping to any other node. So that would make this graph actually not sparse. It would actually be dense. And if you construct a dense graph over, I think there are about 25,000 elements in the matrix you're working with, you probably will hit, you wouldn't quite hit memory limits, but you're getting pretty close there. So don't do that. There's much better ways that you can do that multiplication without constructing a dense graph. But conceptually what we're doing is we're forming a combination of this P matrix. That's the one that has 0 columns splits with 1 and normalized. And when I say normalized there, I mean normalized to have unit norm. To have unit sum, importantly. I mean that we divide by the sum of the elements in that column. Yeah.
Where it says that 1, 1 transpose, that's not normal, right? That's a vector of 1 and then a vector of 1 transpose. So it's a matrix form 1?
Yeah, so 1, 1 transpose, and I'm writing it this way kind of actually to give you a little hint on how you might implement it. 1, 1 transpose. This is a vector of 1s, a column vector. This is a row vector of 1s. So this product here is a matrix of all 1s. Yes. So I think your answer is yes, but I'm just sort of writing what I mean by that.
You could just use element-wise addition. Just get rid of it.
Yes, you could, but I'm writing it that way for a reason. And you may, if you do the 688 problem, you may see why I'm doing it that way. Yeah.
What's the effect of normalizing the columns?
Right. So the question was, what's the effect of normalizing the columns? And importantly, I should probably have put this there because I just say normalize columns there. I am normalizing columns to have the sum of the column always equal to 1. Now remember, they always have positive entries still because everything here is positive. And I'm making the sum have of this row be 1. What this does, and I don't want to get too sort of technical in terms of the terms, but what this does is this makes every column of the matrix a probability distribution, right? Because it all sums to 1. And when you combine probability distributions, you get more probability distributions, right? My x vector is also always going to sum to 1. And what that means is that my product here, x times p, is also going to always sum to 1. And so what this does is this keeps this vector x as always a probability distribution. So that means that what I'm doing here is I'm sort of simulating for what's going to happen when I follow this random process. And making sure that these columns are all normalized to 1 ensures that my vector is always going to be a distribution over which node I'm going to be in at every time. If I didn't have that, then I would be sort of giving unfair weight to nodes with a lot of outgoing edges, and I'd be inflating kind of the effect that those nodes were having. Over there.
So if we just try to find the same thing,
Yes.
Why can't we do that directly by finding the matrix and that solving that?
So the question is, why can't you just directly find the stationary distribution of this Markov chain? Don't worry, if you aren't familiar with those terms, doesn't really matter. The way you find those distributions is through an eigenvalue decomposition, and this is the best way of finding the biggest eigenvalue. Yeah.
The columns of table 1 first. We're only supposed to replace the columns which have all zeros or columns which have some zeros and some ones. And how do we go about doing it without actually replacing them?
Yep. Okay, so the question was, first of all, do you want to replace all the zeros or just the columns that are only 0? It's the second. It's just the columns that are only, the full column is only 0. If a full column is only 0, that means that node has no outgoing edges, right? That's how we encode the adjacency graph, adjacency matrix. And so that is encoding, that step there, replacing it with 0, is encoding this this third line here in the algorithm. Namely, if the node has no outgoing edges, that means its column is going to be all 0, which means we need to replace it with all 1s if we're going to simulate this process of then jumping to a random other element in the graph. As to how you do it without doing that, you could actually do it. You could just replace them in the homework. It'll work. It'll be a little slower. So I'm not going to say that. I'll let you sort of figure out if you want to play around with it a little bit. You do it similarly to how you would do a more efficient version of not having to add a 1 to every element there. So I'm forming a matrix here that is full, right? Because this matrix has a 1 transpose term in it. But I'll tell you right now that you should not form that full matrix, p hat. You should try to figure out a different way of doing it if you're doing the 688 problems. All right, so let's come up with an example here. So here is our directed graph now, and we want to know what's the most important, what's the most highly ranked nodes here. Does anyone want to guess? It doesn't have the notes in front of them. What do you think the most important node in this graph is? It's not super clear, right? But you can see, okay. Any other answers? A, B, and C. Okay. Let's see. First of all, this is the P matrix. This is just the adjacency matrix that I've formed by taking this matrix, normalizing the columns. So the adjacency matrix here is just 1, 1, 1, 1, and all zeros. So what I did was I normalized these to have sum equal to 1. So these stay the same because they just have one element, so their sum is still 1. These are divided by 2 because they have 2 elements here. This has nothing in it, so I replace it with all 1s and normalize that. So it becomes the all 0.25 vector. Now I take this thing and I multiply it by d, where d is 0.9, and I add 1 minus d times the all 1s matrix. And that gives me this. And someone can verify that I'm hopefully correct in writing that. I might be wrong. It's actually, and importantly, it's the 0, 1s matrix that's also normalized itself. So it's the normalized 0, 1s matrix. So it's actually the 0.25 everywhere matrix. I add d times that, right? Because remember, this matrix is not just 1s. It's actually d over the number of vertices times the 1s matrix. So like you get, for the entries that are 0 here, you get 0.025 because the 1s matrix is really the 1s times 0.25 times 0.1, which is 1 minus d. And if I do this a bunch, I get this. So this is A, B, C, and D. And as people were right, C is in fact the most important, or one of the most highly ranked vertices here. Yeah.
Is there an intuitive explanation for why A and D are equally ranked?
why A and D are equally ranked. They actually are exactly the same. So those numbers are exactly the same. I don't know if there's an intuitive explanation other than just when you, that is the distribution of this chain. The way I would sort of see it is they can both only be reached by C. So C has some importance and it can direct them to A or D. When it goes to D, it sort of restarts, so everything kind of resets. And if it goes to A, that's sort of the only other way it could go. And then now being in both A or B, it has some probability of coming back to C, which is why C is a little higher, because C can kind of have this loop and it leads somewhere else, which is sort of the intuition there. I would hesitate to ascribe too much intuition to this, because this is sort of a contrived example and it's not really the important ones. And these are all pretty close anyway. It's just sort of the numbers you get when you run this. So that's how I would describe it, but I'm just making it up on the spot, so it sounded reasonable, right? Okay, any questions? Yeah.
So why do we choose D? Why not just keep it at 1?
Yeah, so that causes this problem we see here. So here it wouldn't really matter, but in general, D equals 1 will cause this problem. If you have a bunch of edges pointing into a node, and then a bunch of chains that sort of follow from this node, because you always go from here to here, and then from here to here, and here to here, if I end up in this node, I definitely am always going to hit all of these too. So this would prescribe the same importance to all of these as it does to this one, which seems wrong to me. I don't know. It seems wrong to me. So I would say we shouldn't do that. But if you want to set D equal to 1, you can. Just be a different ranking. All right. Moving right along, but hopefully we get to a little bit of natural language processing today. If we don't, it's not that big a deal. Well, we'll get to a little bit, because we'll finish it in one lecture certainly, but we'll definitely finish by next time. But I hope to have 20 minutes to talk next time about geographic information systems. Okay, let's talk about the last algorithm then, which is community detection algorithms. So these really sort of got a huge boost in popularity with the advent of social networks, right? And the idea here is that in many graphs that we see in the real world, there seem to be kind of tightly knit communities. So these are edges where the connectivity amongst members of that community is much higher than between much higher between them than it is from between them and other people that are outside that community. And this is sort of a fake example here, but a lot of graphs do have structure that looks like that in practice. So think about friend networks on Facebook or something. These networks, oftentimes friends of friends are all friends with each other too. And these are much more tightly knit than say, us and someone across the other side of the world, right? They'll have their own friends, we'll have our own friends, and there may be one link or two between the two, but our own communities are much tighter than this, right? This is a very common phenomenon in a lot of real world graphs. And this notion of community is actually a soft version of what's called a clique in graph theory. And a clique is a fully connected, or clique sometimes, but clique is usually how I've learned to pronounce it. But a clique is a fully connected subgraph in the network. So I think this one here, this community here would actually be a clique because it's actually fully connected. There's a node from every member in the community to every other member. But communities are kind of a soft version of that. So they can be full cliques, but they don't have to be. There could be one or two missing edges, and we still call it a community if the entirety of that is more connected than it is to the outside. So the Girvan-Newman algorithm was kind of one of the foundational algorithms in instantiating a lot of research in topics like communities in large graphs. And again, it goes back to ideas that have been around for a lot longer, but and since then there have been much faster algorithms proposed for this, but it's still a good algorithm to sort of know about for both simplicity and for historical reasons. And here I'm going to go at a much higher level because actually describing the algorithm, how you would implement it, does require a little bit more detail. Specifically, there's going to be this notion of betweenness of different nodes in a network, or actually on edges in a network. And computing that in an efficient way is not completely trivial. And so I'm just going to actually kind of gloss over that, and I'll define it, but I won't define how do you actually compute this quantity in an efficient manner and update it as the graph sort of breaks down into communities. But the basic idea is very simple. The basic idea is instead of trying to kind of identify the communities by kind of the bottom up, this kind of takes somewhat of a top-down view. And what we're going to do is we're going to take edges in the network, and we're going to progressively remove edges from the network. So we're going to start taking out edges based upon a property called their betweenness. And as I take out edges, occasionally I will split the graph. I will break it into two what's called connected components. There's going to be two independent graphs that are not connected to each other. And once I do that, we say that those two components form two different communities. Then I hierarchically, or recursively actually, break down each of those subgraphs and repeat this process. And what this actually creates in the end is a whole hierarchy of communities in the network where the breakdowns at different levels describe communities at different sort of levels of granularity. So hopefully that was somewhat intuitive there, but I'm going to give an example in a second, which hopefully makes it a little bit more clear. But now a little bit more formally, what I'm actually going to do is I'm going to compute a factor on each edge called the betweenness of that edge. And the betweenness, despite PowerPoint telling me it was not a correct word to spell and constantly underlining it in my slides, it's the actual term. Betweenness is very simple to define, kind of a little harder to compute, but the definition is just, it is the number of, if I take the entire graph and look at all the shortest paths between all pairs of nodes, the betweenness of an edge is just the number of paths that pass through that edge of all these shortest paths. Okay, so hopefully I'll be a lot more clear when I have an example, and I'm going to have an example in a second, so maybe I'll just go to that very quickly. But then what we do is we remove the edges with the highest betweenness. And if this breaks the node into two different subgraphs, we recursively partition each one until we're only at singletons, and then we have our full hierarchy. And so I'll show you what that actually looks like. How you get communities from that is not completely clear maybe, but I'll show you how you actually, what this looks like. Yeah, there's a question?
Yeah, I mean, if we take some vertices which are in one community,
yeah,
and there is a lot of shortest paths between them, and it will contribute to some edges. The total contribution of this pattern will be much more than if we take two vertices which have the unique shortest.
Yeah. So the question was, if you have multiple shortest paths between the two, then their weight's going to be higher by this. So yes, betweenness actually normalizes by the number of paths that are all the same length. So you take the shortest path, but if there are multiple shortest paths, you only count each one the fraction according to how many shortest paths there are. Again, you don't actually compute it that way, but that's the idea. Yeah. Okay, so here's an easy graph to partition. So we're going to partition this one with the Girvan-Newman algorithm. So you might imagine, right? The communities in this graph probably are, well, first it's probably the left half and the right half, and then it's probably these clusters there, the top left, bottom left, top right, bottom right. But let's see how this actually works with the algorithm. So the first thing we're going to do is we're going to compute the betweenness between all of these. So one important thing to note here is that this is just going to give you a sense of it. So I mean, if you had to compute betweenness by actually computing all shortest paths and taking their distance, that would be very expensive, right? Because you have to compute all shortest paths and then actually compute these distances and then count up the number of total paths. But I'm telling you right now that the betweenness of this edge in the middle there is 49. And the reason why it's 49 is that there are 7 nodes on that side and 7 nodes on this side. So every pair of nodes there or there, a shortest path between them has to go to that one link, right? There's no other option. And in fact, whenever you have a network that's connected where two separate graphs are connected by one node, one edge, the betweenness of that edge is always just the product of the number of nodes in this network times the number of nodes in that network, right? Because every shortest path here will have to go through it to every element in the second graph here. So I'm not going to tell, I mean, and actually these are all pretty similar, so that the 33 one is also the case. So there are 11 nodes on this side and 3 nodes over there. That's why that one's 33. When you don't have a single connector, though, it's a little trickier to see why that intuition still holds. So why that node there is 12 and the other one is 1 is less clear. But there are efficient ways to compute this without computing all the distances that you can compute quite efficiently. So, and importantly, you can also update it after you break an edge, right? Because when I remove this edge, I'm going to have different graphs now, and I have to update the betweenness to sort of factor in the fact that these things don't exist anymore. So you have to do all these things, but they can all be done relatively efficiently. And actually, if people are curious, there's some great references on this that I can point to. John Kleinberg has a great book that discusses a lot of these algorithms, including PageRank and Griffin-Newman. So if anyone's curious, I can post a link to that. So anyway, okay, these are all the edges. I'm only the rest are all the same as this. They're just they're all symmetric here, so they all look the same. So this is also 33 here. This is also 12 and 12 and 1, etc. I'm just writing it on the ones that we on a unique set of ones. Then I remove this edge, and I have 2 separate graphs now. I'm just going to keep doing this, and you have to kind of trust me. This is what happens. You're actually allowed to either remove one edge at a time or remove ties simultaneously. People talk about that algorithm working both ways. If you look at the Network X implementation, which we'll talk about in a second, it will actually always remove one edge at a time, not multiple ones, but it doesn't really matter too much. You can remove them all at once. So in this next time, the edges of the highest betweenness, again, just by symmetry, are going to be all the 4 ones connecting 7 and 8 to the other 2 clusters there. So if we remove those, we get this graph. And if we finally do it one more time, we have nothing else to remove, so it's going to be the empty graph. I think I don't actually even have a picture of this. Now, the result of this algorithm, in some sense, is not just communities itself. It is actually what's called a hierarchy or a dendrogram of nodes over in this graph. So here we have kind of the actual result of this algorithm. It is saying that these nodes here would join up at the first level. These would join up at the first level. The next level, these will all join together with these 2 and with 7. And then at the third level, they would all join together. So if you want communities from this, what you can do is you can actually take any given level in this hierarchy and actually just look at the breakdown of clusters in that level of the hierarchy. And that will give you communities at whatever degree of fidelity or whatever degree of resolution you want. Now, how do you pick the correct level there? It's tricky. And sometimes you don't do that. Sometimes you actually just look for groups that have a certain size to them maybe. And you go up the tree until they reach a certain size. And you call that a community. And you do it in some greedy fashion. But there are a lot of ways you can kind of go from this to communities. The harder part is actually getting to here than once you're already here. All right, any questions? Yeah. Why is this 1 and 12 here? Where's the question? It's 1 there because there's only one shortest path between those 2, and it goes through that edge. I'm not going to say why it's 12. It's 12 actually. No, actually 12 is easy. It's 12 because there's 12 nodes on this side, and 1 node over there, and that goes through all 12 of those. So there's 12 nodes, not including 1 and 2. So the path from 1 to all of those goes through that edge 12 times. Yeah, so those actually are all easy in this case. And the 1 there is because there's only one shortest path between nodes 1 and 2, and that's just that path. Nothing else will go through that path, right? No other shortest path would go through there. Yes? The question was, does this computation have something to do with cuts in the graph? I don't think it's quite this. I'm not sure I see a connection, but there may be. I'm just not aware of. All right, so let's finally end this just very quickly now, because this is not too difficult. Or rather, I'm not too difficult, but this is just not that detailed in the slides here. Talking about libraries for how you work with graphs in Python. Question? Okay, the question was, where do you use the community detection algorithms? So a lot of time, these come from social network analysis. And so I've seen a lot of work on looking at, say, Twitter, right? And seeing, are there communities within Twitter that are kind of acting as echo chambers to amplify messages, maybe in a way that Twitter doesn't want, right? So people retweet each other a lot, and their comments get a lot of weight to them, but they're just all talking to themselves. This shouldn't really be happening. This happens a lot with the prevalence of like botnets, right? So a botnet on Twitter will start talking to itself a lot and bumping up its seeming importance very high, or will link to it a lot and then each other a lot, bump up its seeming importance very high, but they're actually all just sort of garbage links. So there is a huge use for these things like communities, both from a social science perspective of just sort of understanding what communities exist in these networks, and from a practical perspective of, can we identify certain regions that are sort of talking within themselves a lot more, or interacting with themselves a lot more than interacting with everyone else. All right, so the library that you're going to work, actually, I don't know if we don't have a problem on this one for the people not in 688. In 688, you will use this a little bit, but you're not going to get a chance to do everything that we cover in this class on the homework. So, and I didn't cover it till this week anyway, so it probably would have been lousy to have it on this next homework at least. The library you can use for handling graphs in Python is the NetworkX library. This is by far the most. There are other ones, but this is by far the most common. It's a pure Python interface, so it does everything in Python. And it has a very large suite of algorithms to do different tasks in, all the algorithms we talked about do have implementations in NetworkX, so you can just call nx.pagerank or nx.Gervin-Newman, and it'll just solve it. One key point, though, is this is not a large-scale graph library. So in particular, it's using a dictionary of using an adjacency dictionary representation for the graph. And it doesn't always even have the most efficient implementation of its own algorithms. So for example, on the homework problem for 688, it cannot run PageRank if you run it on the size of the graph you have. Because it runs PageRank actually using the dictionary representation as well, not the adjacency matrix representation, which is what you should do to run PageRank. So just know that it's great. If you have a small example, it'll always work, and it'll be fast enough that it won't matter. But if you have large graphs, it both will take a long time to store these things, because dictionaries are not the most efficient way of doing it. Matrices are a better way of doing it. And sparse matrices are probably a better way. And it's actually oftentimes the algorithms themselves use the wrong internal representation, and so they are actually relatively slow. Not always true. Its Dijkstra's algorithm is very good, actually, incidentally, but its PageRank is not very good. And just there are a huge number of algorithms in there, so they are going for coverage rather than optimizing any particular one. It's also all native Python, so I believe. Not that for sure, but most things that are native Python at least. There may be some C optimization in there somewhere, but for the most part, it's all native Python, so it's not sped up the level of C libraries would be. Okay, so I'm just going to walk through this very quickly here. A notebook with all this code is on the website, so you can download it, you can play around with it. I'm not going to actually bring up a notebook here separately either. I think I just want to highlight some of the main functionality of the library, and you can explore it yourself. You create a graph with a .graph call. I import NetworkX usually as NX to abbreviate it. You can create an undirected graph or directed graphs. And then you can add and remove edges from this graph. So there are a few ways you can do this, actually. You can also add nodes separately. But if you add an edge between two nodes, two named nodes A and B, it will actually also create those nodes too. So you don't have to worry about creating nodes separately from edges. You can just add edges. That's usually the easier way to do it. So the most common call I'll use to construct a graph is the add edges from. This takes a list of edges where edges are specified as tuples, the from and the to in the tuple, and it will create a graph with those edges. Again, it will create the nodes as needed to do those. Nodes themselves can actually be any hashable type. So NetworkX uses the adjacency dictionary representation internally. So the identifier for a node can be any type that you can use as a key for a dictionary. You can also remove edges. Remember, it's using a dictionary, so it's very fast to remove. There are commands to remove from a list. You can remove a single one. You can add a single one, etc. It all sort of is easy. So this goes through a few operations and eventually makes the graph back the way it was. They're all the same functions for removing nodes and adding nodes. The nodes initially, if you add them that way, would just be without any edges, but you can also add nodes. So if you have a node with no edges connected to it, you can add it that way with add nodes. If you want to see what it's doing internally, you could just call the graph, the brackets, and the node name, and that will return a dictionary of edges that node is linked to. This is in fact exactly the internal dictionary of adjacency dictionary implementation that it's exposing here. And the way it does it actually is it says that each element there points to an empty dictionary or an empty dictionary itself. So I think in my version that I described, I had the value of the second key was like 1.0, or the weight of the edge if you have a weighted graph. But NetworkX actually has those as separate properties. So the actual value here of G, C, then if you put A in brackets again, it would actually be an empty dictionary where you could encode other things if you wanted to. You can iterate over the nodes and edges using the g.nodes and g.edges functions. At one earlier point in the library, you would want to use a different call to get an iterator versus a list of the nodes or edges. But I think in the current version, those have been, at least in my version, those have been merged. So g.nodes always returns an iterator. And so just use that. This is sort of actually moving towards more like Python 3 representation, where they get rid of the things that return lists for the most part, and just everything returns iterators. So in the latest version at least, regardless of what version of Python you use, the .nodes and .edges return iterators that iterate over the edges and nodes. G.nodes will loop over the node names, so the individual element there will be a single node, and then G.edges will return an iterator over tuples. So if you want to find each individual edge, you'll extract the elements of that tuple and see that there's a node, an edge from node I to node J. In a undirected graph, a node from I to J implies also J to I, but it will only store one of those oftentimes. So you will only get, if you iterate over the edges, you'll only get one direction. You won't get both directions. Just as I believe, I'm pretty sure about that. I think I did most of my tests here with directed graph, but I'm pretty sure you will only get one edge. I'll test that, and if I'm wrong, I'll issue a correction next time. You can also set node and edge properties. So one interesting element of NetworkX is you can also kind of add whatever information you want, whatever data you want, to a node or to an edge. In addition to just its name, you can also add, what's its weight, what's its color, what's anything else. And the way you do that is with the g.node call. You couldn't just add something to this because g brackets a actually refers to the edge. So you can't do that. You actually can do it for edges. That dictionary up there is actually the dictionary of properties for the edge. So you actually could leave out the edge term here, but I like to leave it in just for consistency. So g.node of the node, and then the property equals some value. G.edge of the first edge, second edge, and the some edge property name equals edge value. That adds a property to the edge between A and B. The first one adds a property to the node A. And then if you want to get the properties back, when you call g.nodes, you have to pass this data equals true flag to the function. And that will return an iterator where it also returns a data property for each node and a data property for each edge. I think I have two more slides. Drawing nodes. So you can draw nodes too with Matplotlib and NetworkX. They look really ugly. I don't know why they choose this for the directed graph notation, but this is our graph that's drawn there. It actually lays them out using a reasonable algorithm and then picks really small, ugly sizes and Those are directions. This is an arrow. This big bar here says that this points from there to there. I don't know why they use bars instead of arrows. Maybe they're easier to draw. There are a lot of other routines inside that will use some other graph drawing library on top of NetworkX to draw them very nicely. So GraphViz is one of these that's very common. So you can actually draw very nice drawings through NetworkX, but the default .draw command does not do that. But you can still use it for your own sake. Just don't include these along with visualization, right? Same lesson applies where it's fine to use for your own exploration, but don't try to convince anyone of anything with a figure like that. And still save it as PDFs. Even if you do this ugly, just save it as PDF still, not as a PNG. Okay, so now finally, I'll just highlight the fact that yes, there are lots of algorithms in NetworkX. You can, for example, do the entire 688 homework with 2 calls in theory. Just shortest path length would give you for graph G and the source equal to A. That would give you all the shortest paths. That's actually just the length. There's another thing called shortest path that will give you the actual paths themselves. And x.pagerank for G, and they use alpha instead of D. I'm not sure why, but they use the parameter alpha. And that runs the PageRank algorithm, returns a vector that returns a dictionary that says for each element, for each node, here is its PageRank. And then Girvan-Newman also will actually return an iterator over partitionings of the graph. So it sort of partitions them iteratively, and it will return this iterator that does that. That one actually only exists in the current dev version of NetworkX, so it will not run if you have the Anaconda version. But you can run this command over there if you want to try it out. You don't have to. Actually, that one is not required for the homework. But if you want to, it's there too. OK, so with that, we finished the material from last lecture. So now we can start this lecture's material. Any questions? Yeah.
It's one question about the page run. So actually, we have to iterate our operation. I mean, our steps of multiplication by this random matrix. So, and how many steps do we iterate?
Oh.
We didn't put it in a function. So
Yep. So the question is, in PageRank, how often do you iterate? So the question is, you're multiplying by this matrix again and again, right? And the goal of this process is actually finding the stationary distribution of this process. And the number of times you need actually depends on a lot of sort of mathematical quantities here. Just do 100 times and you'll find it. For most reasonable graphs, that's plenty. Okay, so taking a little breath here. I'm sorry, was there another question? Let's see. Okay, taking a breath here. We're kind of marching along in this quest to sort of cover a bunch of different types of data that you will encounter as a data scientist. We talked about relational data. We talked about visualization, which isn't quite the same, but related. We talked about graphs. We talked about matrices. Now we're going to talk about another type, which is extremely common to find in practice, and which doing it in its totality is incredibly hard, but which fortunately we can kind of cheat on a lot of times. And that is free text and natural language. So oftentimes when you're doing data science, maybe I should just jump through what we're going to talk about. Actually, I have some intro in this first section, so maybe I'll start when I talk there. But what we're going to talk about first is kind of a broad introduction of free text in data science, and what I mean when I say free text analysis or natural language processing, and I'll use that in quotes right now, even though I hate air quotes. I'll say that just because it is not real natural language processing. It is very, very simple methodologies that let us extract some information from free text. We'll then talk about, again, probably getting through this maybe today, but not the later ones. We'll talk about bag of words methodologies and a type of encoding called TF-IDF, which stands for term frequency inverse document frequency. We'll also talk about language models and n-grams. For the homework, in fact, you will, or the 68 version at least, will implement a language model. So you'll get to generate text from some fun language and see kind of the fun sentences it gives you. And then next time, definitely next time, though a lot of this will also be next time, we'll also talk about libraries for doing this in Python without going through too many of the details itself. Okay, so let's first talk about free text and data science and what I mean. This is kind of my own philosophy on this. I'm not sure how widely shared this is, but I'll tell you my view. So the first thing to say is that a huge amount of data that you will encounter if you do data science is in free text. So, there will be some comment field in your database that sort of says, comments on this particular row. So comments on the student, right? Comments on the grade for this assignment. And that's entered by, someone, the student, the TA, whoever, right? It's just entering whatever they want, and it'll be shorthand, there'll be typos in it, it'll be a mess, but it will be very valuable in some sense, right? It should be valuable. We should be able to extract some information from this sort of vast wealth that we have of human written text, which is sort of meant for other humans to consume, not for computers to consume. And the entire field of natural language processing, at least the computational version of natural language processing, is really centered around the sort of maybe fundamental and biggest challenge possible of understanding natural language, right? So if we can solve that, I mean, that is essentially solving AI, right? If a computer could understand all natural language, it's probably, have solved artificial intelligence. Now, we are not going to solve AI here. We're not trying to do that in a data science course. But it sort of does raise a question, right? Is if natural language is so complex, and I'll give some examples in a second that are always fun to consider about, why natural language is in fact so hard. But if we're already admitting this is sort of an AI hard problem, right? You can't solve it until you solve AI. Then what are we going to do instead? And what this lecture is about really is a few tricks that we have, and I'll kind of call them tricks unremorsefully, to try to get some information out of these free text fields, right? So if we have a free text field, we're never going to be able to define exactly what the person meant and translate it, to a beautiful object schema that the algorithms can process perfectly. But maybe we can get a little bit of information out of it. Okay, so that's the goal for this lecture and next lecture too. Not to solve NLP, but to get some information out of free text. So the problem, of course, is that understanding languages is hard. So there's many examples about why language is a fundamentally ambiguous thing. Like a quote from Groucho Marx that says, "While hunting in Africa, I shot an elephant in my pajamas. How he got into my pajamas, I don't know." And the reason why this is funny is that, if it's that funny, I don't know. It's from the 1930s, I think, so maybe it's not that funny anymore. The point being is that you can parse that sentence, that first sentence, in multiple ways, right? You can either ascribe the wearing my pajamas or in my pajamas to the elephant or to the person that shot the elephant. Maybe it's not good to talk about shooting elephants anymore, too. I don't know. This is from the 30s again, so maybe it's less appropriate these days. But this happens all the time, right? Another great example of these are what are called Winograd schemas. So these are examples where there's a sentence where if you change one word, you will just naturally interpret it one way or the other way. So sentence here is, the city councilman refused the demonstrators a permit because they feared violence. If you say feared violence, you are implying that it is the councilman, that they refers to the city councilman. If you say they advocated violence, you probably mean that they refers to the protesters, right? And so the upshot of all of this is, and similarly, if you read the first sentence without the joke that Groucho Marx puts on afterwards, you probably would assume that he meant he was wearing his pajamas, not the elephant was wearing his pajamas, right? And the point of this, of course, is that they're the same sentence. There is no difference in those two sentences. Other than one word, which has the exact same part of speech, everything's the same. The only difference is that you know from the context, from the actual meaning of the words, you know what's intended, and so you know how to interpret this sentence. And this is incredibly hard, right? It's very hard to encode a set of rules that can do this. We use an incredible amount of context when we hear and understand language. And this is highly non-trivial to encode in a program. But of course, the question is this really always that hard? So here are two reviews that I pulled from Star Wars. I think I got them on Rotten Tomatoes, the review site. And the first review says, truly a stunning exercise in large-scale filmmaking, a beautifully assembled picture in which Abrams combines a magnificent cast with a marvelous flair for big screen sci-fi storytelling. And the second one says, it's loud and full of vim, but a little hollow and heartless. So you can probably guess, without me showing you the actual star ratings on these two things, which one of these is positive and which one is negative, right? And it does not require, and you aren't doing it, I would say, because you sort of are parsing that whole ridiculously long sentence up there with multiple clauses and lots of grandiose phrases there. You're doing it because you can pick up on certain words, right? There are just certain words that tell you what they actually think about this movie. It's stunning, magnificent, marvelous, versus hollow and heartless, right? So it's pretty easy, in this case at least, and we'll show some cases why this is not true after I make this argument. But it's oftentimes very easy to look at the overall text and get a gist of what it's saying without actually understanding the sentence structure of this natural language sentence, right? Not always. Sometimes, they'll have a clause that's negated by the very last word in the sentence. If you say, on all that was not true, that was the opposite of what I mean. You can always do that, right? But we don't usually write like that because we're not trying to mislead people or trick people. We're trying to convey what we mean, and so we oftentimes write in a way that actually expresses what we mean as we write it. And this is going to be kind of the key for us, because oftentimes getting some information out of natural language is actually quite easy, and we can do it with very simple methods. And these serve as a much simpler and faster way to try to get information out of this. And so what I'm going to talk about in this lecture, or in this lecture and next lecture, is two simple techniques that can be used for getting some information out of free text data. And these are going to be what are called bag of words approaches, which is a great name, and it implies, as you might imagine, that the ordering of words doesn't matter. All that matters is the presence or absence, or maybe the count of words in a document, because it's like a big bag of the words of that document, along with something called term frequency inverse document frequency models. And secondly, I'm going to talk about n-gram language models, which are now a method that does take order into account, but does it in a very simple way that lets us infer some information, but also which misses obvious context, and so is not really providing a full model, but a model which is useful nonetheless. Now, one thing I'll add to this is that this lecture, probably more than many others, I would not bet on it being still relevant, say, 5 years from now. So there's been a huge amount of progress in kind of off-the-shelf techniques for natural language processing. These are largely involved techniques from deep learning, like recurrent neural networks, which we'll talk about much later. But it may very well be the case, and we may already be getting there, where the best thing to do if you want to understand natural language is not to use one of these approaches. Well, maybe you still should use them first, but we may be into a point where very soon after that, you can actually just apply some of these rich language models that people have developed using deep learning approaches, and those provide actually better representations than these things here. Well, they certainly are better, but they may someday soon become as kind of off the shelf as these things here. This, by the way, has already happened with images. So we'll talk about images a little bit later in this class. But the reality is, when you want to process images these days, you should go for deep learning methods. You should just use those almost right off the bat before you start trying other things, because they are so much more powerful than other techniques that have been developed, that you should just use them. And the same may happen very soon for natural language, so I would not bet on this lecture being as relevant as other ones. I guess I wouldn't bet on even being relevant 10 years from now, right? Who knows what's going to happen in 10 years? Hopefully they'll still be a little bit relevant. But I would not bet on this one. The odds on this one would actually be very low, I think. Maybe for historical reasons they'll still be interesting in some of these things, but I don't think they'll be, I suspect they will be outdated faster than other elements. Okay, so I'll just get started very briefly on bag of words. Any questions before I start? I'll get started very briefly on bag of words. But before I start, I want to mention a few quick terms. I'm going to use the word document frequently in this lecture, and that in this context means some collection of text. It could be an actual document. I mean, it's not, it could be an actual file on a system that makes up a document. Or it could just be, say, a text field in a relational database, or in some table in a relational database. That would also be a document. So document kind of means just generally a collection of words that are strung together in natural language, right? As short or as long as need be. The term word or terms refers to individual words. I realize that that's circular, but what I mean by words is tokens separated by white space, but also oftentimes things like punctuation. So a period in this context actually could be a word, right? So in fact, in the 688 homework, you'll be building some models, and their periods will actually be themselves tokens or words in your lexicon or your dictionary. Okay, so the bag of words approach is it's a great name, as I said before, but it kind of is the word cloud view of documents, right? So we have a document written in natural text. It has all sorts of very interesting meaning. The sentences are grammatical. They have to make sense. They have to have subjects and objects of the sentence. They have to have actions, all these kind of things. We're going to take all of this and we're going to just throw it all away. And we're going to describe a document entirely based upon the words that occur in that document and the number of times they occur. Right? So this is essentially like a word cloud. So if I create a word cloud of our class webpage, you see this. So clearly data is a central concept in this course because the word data occurs a lot of times. And so what the bag of words says is that don't bother reading the website, just read this word cloud because it has all the information you'd want from the website. So hopefully you don't take that advice to heart. That's just emphasizing just how much we're throwing out when we go this route. And as you may imagine, the way you do this is you just, we don't do it actually with pictures like that. That's just a visual picture. We're not going to convert all documents to images. What we're going to do instead is we're going to represent each document as just a vector of word frequencies. Again, the order of words is irrelevant. All that matters is how many times a word occurs in the document. So I'm going to have, in this example, 3 different documents. The documents say, the goal of this lecture is to explain the basics of free text processing. Second one says the bag of words model is one such approach. And the third one says text processing via bag of words. Very interesting documents, as you can tell. So the way you would encode this is each row in this matrix now is going to encode a term frequency count for one of these documents. So the first row is going to encode document 1. The second row is going to encode document 2, and the third row is going to encode document 3. And all the entries are, and then each row in the matrix is going to correspond to one of the words. And there is a row for the union of all words that occur across all documents, right? So if any word occurs in any of the documents, there's going to be a row in the matrix corresponding to that word. So, for example, the word the appears twice in the first. I hope I got the numbers all right. The word the appears twice in the first document, and once in the second one, and 0 times in the third one. The word is appears once in the first, once in the second, and 0 times in the third. The word of appears once in the second, twice in the first, once in the second, and once in the third, etc. The word lecture appears only in the first document. The word bag and words appear in the second and third, etc. Right. So we sort of go on like this. This is our encoding of a document in the bag of words approach. So each row of this matrix corresponds to a document, and we are throwing out all the other information about where these things occur. And in particular, the word, the term frequency, just refers to this count of how often a word occurs in the document. It's kind of based on there actually are words for all these things, but this is the term. It's called term frequency. And we're going to denote it with this TF sub ij. And TF sub ij, here and elsewhere, will just denote the number of times that word J appears in document I. So TF IJ equals number of occurrences of word J in document I. And I'm ordering it that way so that these things correspond to the same order that we have in our matrix. So the rows index over documents and the columns index over words. And the last thing I'll say before we finish here is that there are though it seems very simple, the raw count of words is one way to represent this. There are other ones as well. So oftentimes you will also see, say, binary term frequency matrices where does this occur or not, regardless of how many times. You might see log smoothing, or you might see them normalized by the number of times that term occurs in the document. So we'll pick up here next time. We'll hopefully have a little smidgen of time for GIS data, but we'll definitely finish this. And so we'll then, after next lecture, move on to analytics.